Okay, we are on the last couple of pages in this section prior to the notes, the active session and the exercises. So we're going to wrap this up actually fairly quickly. Homogeneous systems of equations are those systems of linear equations where all the right-hand side is set equal to 0. Now, with any system of linear equations, no matter what it has on the right-hand side, there is always a homogeneous system that's associated with it. And it's the one you get by setting the right-hand side equal to 0. Now that might seem a little bit silly, but it turns out actually to be a useful idea, and we'll talk about that in a bit. Now, one thing that we want to point out is that a homogeneous system always has a solution. You cannot get the no solution option with homogeneous systems. And the reason is that these right-hand sides are zeros. So notice if I set x1, x2, and x3 all to 0, no matter what the coefficients are, that's going to sum up to be 0, right? Same thing on this row, same thing on this row. So it is guaranteed without any calculation. We know that 0, 0, 0 is a solution. So you can't have an inconsistent homogeneous system. Now, that means that we know in general there are three possibilities. A system of equations has no solution, exactly one solution, or infinitely many, and we've just tossed out one possibility. No solution isn't possible with homogeneous systems, and therefore if you're looking at a homogeneous system, it has either a unique solution or it has infinitely many solutions. Now, this solution, because it really takes no calculation to figure out that it works, is known as the trivial solution. It's the trivial solution, of course, of a homogeneous equation. If this were non-homogeneous, it wouldn't be obvious what the solution is, or if there is one, you'd have to do some calculations. Now, I put this in the notes and I kind of regretted it later. This is a true statement. Any system with two distinct solutions has to have infinitely many. And I tried to give a little bit of an argument here for that, but I would recommend that for right now you just skip that. And the reason is that we're going to come back to it in the next section anyway, and it'll be much easier to understand after we have a little bit more, a few more tools available to us. Now, so we know some stuff about homogeneous systems. There are some things that you really should have committed to memory here. The first one is this, Theorem 1, any system of linear algebraic equations has one, none, or infinitely many solutions. No other counts on solutions are possible, but we've said that before. A homogeneous system of linear algebraic equations has either exactly one or infinitely many solutions, so the no solution option is gone, and we talked about why that's true. If you set all the variables to 0, you obviously get a solution. And now we'd like to give some geometric insight for why that is. All right, now think about if you have, say something like this, 3x plus 2y equals, 12. Now there is a linear equation, right? And you can solve this for y if you wanted to. Y equals, let's see, we'd have minus 3 halves x and plus 12 divided by 2, 6. So, oops, lost my x right there. So, the graph of this equation is a line. It has a slope of minus 3 halves, so kind of like that. Top leans over to the left, and it's got a positive y-intercept. Now, the point of this is that if you have two variables, if you have a single equation in two variables, its graph is some kind of a line. Now, what line, I don't know, but it's going to be a line. And now if I take another one of these, I get, if it's got a different slope, then it is guaranteed that there's going to be a point in common between these lines. Now, a point is an ordered pair that satisfies the equation. So it's a solution to one of those equations, right? And if you have a point that lies on both lines, then it's a solution that satisfies both equations, and therefore a solution to the system. So if you have two variables, and those two lines are distinct, then you can see how the situation of one solution could come up. A unique solution would be just two lines that have different slopes. Now, what else could happen? Well, you could have two lines which are in fact different lines, but they have the same slope, right? Well, in that case, there are no points on this line that are also on this line. So this would be an example of no solutions. And the third possibility is this, is that you have two equations, but they're one in disguise. So for instance, you have 3x plus 2y equals 12 for one of your equations, and then maybe multiply this by minus 1. Minus 3x minus 2y equals minus 12. It looks different, but it really is equivalent to the first equation. So if you drew the graph, one line would be right on top of the other, and any point that's on one line is therefore on the other, and therefore there are infinitely many solutions, and geometrically that's all that could happen, right? Now, let me just push this one little step further, which is this. Suppose that you had a homogeneous system. So let's say we had this, 3x plus 2y equals 0. I'm just making stuff up here. How about this, 5x minus 4y equals 0. Now, notice in this case you can solve for y equals 5/4 x, and here y equals minus 3/2 x. The point is there is no constant term, so so any such lines have a y-intercept of 0. They have to go through the origin. So no matter how you pick these lines, they are guaranteed to share one point in common, namely the origin. Therefore, you cannot have, with a system of two equations and two unknowns, it is impossible to come up with one that's homogeneous and has no solution. The reason is the origin, geometrically now, not from calculation, the origin is guaranteed to be a common point of all those lines. So looking at the situation geometrically is really kind of valuable. Now, the last thing would be, could we do that with three variables? And the answer is yes, but it's an awful lot harder to draw. First of all, for no solutions, that is not hard to come up with at all. You can just imagine, well, can I draw anything that sort of suggests a plane? You could have three planes, but whoops, I'm trying to make this just look like that. And the idea is that that these three planes are stacked up one over another. So for instance, just think about a piece of paper. I've got a well, that's not going to work with this camera, is it? So imagine this. This happens to be a battery, but anyway, think about that surface. That's a plane. If I just move it over in a parallel way, that's another plane, that's another plane. You could easily come up with three planes that don't intersect. They're just all parallel. But it's more complicated than that. You could have, say, this plane and then another that's parallel, and then take another one that slices through it. So, you have planes. I'm waiting for my camera to catch up. There we go. So we got planes here, and one that slices it. Well, these two planes have a whole line of intersections. These two planes have a whole line of intersections, but there is no place where the three planes meet together. So there's lots of ways for the no solution case, but geometrically it's easy to see that that could happen. You have no solutions. Now what about a single solution? That actually is not very hard. If we were to take, let me see, a phone might make a good plane. Take a plane here, and then take a plane here. So these guys slice each other. They're going to intersect along a whole line, right? So this one and this one. And now take another plane and slice right through the middle. So these two intersect with a line. So I've got a line here, and then I slice that with a plane that's not parallel to either one of those other ones. It's going to hit in a single point on that line of intersection. So, whoops, these two planes meet along a line, and then I slice. Well, how about down here at this piece of paper right here? I get the cross section is this, and then you slice this way, you get a single point of intersection. So it is easy to come up with an explanation for one solution with three planes, so three equations and three unknowns. As a matter of fact, if you want to see that, you look like at the corner of a room, and I'm sorry, I have virtually no ability to draw, but so we're looking like at a box, right? So there's a plane here, there's a plane here on the end, and then there's a plane over on this side. So so those three planes, the top, the end, and that side, meet at a single point. So there's a case for a single solution. Now, how could infinitely many solutions occur? Well, it turns out there's quite a few ways. One, of course, would be just like with the two-dimensional case, where you just have three equations that are all equivalent. So they're really naming the whole plane, the same plane rather. So you sort of could get that idea. This piece of paper, sort of think of that as a plane, and then I just disguise it by its equation by multiplying through by 2 or something. That gives me the same plane, so those two are the same. And then I multiply it by -1, and now I've got those three planes. They're right on top of each other. They're the same plane. That gives me a two-dimensional surface of solutions. All the points on any of those planes are in parallel, two-dimensional, infinitely many. But it could happen another way as well. How about this? The pages of a book. You have, let's see, this thing just opens up, right? And you can kind of get the idea that I have a plane here. Whoops, a plane here and a plane here that intersect in a line, but there's no reason you can't have another plane that intersects in that same line. So they all meet at the spine, and therefore I could have not only a two-dimensional surface, which is the intersection of all the planes, I could have a one-dimensional line, which is the intersection of all the planes, and that again is infinitely many solutions. So for infinitely many, there's some variety here. It could be two-dimensional, a plane, or it could be one-dimensional, a line. And that's something that you can see by calculation as well. When we did this one that had infinitely many solutions, this is example number 2, I got one parameter, so I have a one-dimensional line that is the solution. It is all the solutions to this system of equations. And if I had gotten two parameters, say an s and a t, then that would mean I have a whole plane of solutions. Now, with when we're calculating and not trying to imagine shapes, there's no reason that you have to stop at 3 dimensions, right? You could have 17 variables. And if you have 17 variables, it's possible that you could have a hyperplane of, say, 5 dimensions, which every point in that hyperplane is a solution to the system. Well, it's still infinitely many, but it's infinitely many in a different way. So this geometry really does kind of help in the sense that we realize there's some subtleties here when we say infinitely many. Yeah, well, infinitely, how infinite? You know, 1-dimensional infinite, 2-dimensional infinite, 7-dimensional infinite. Those are all possible with different kinds of systems of equations. Well, that is it. The MATLAB Octave session is here. I've told you where you can grab that. Exercises are here. There is a hand-in homework that is to be submitted by next Tuesday at class time. And if you look in the week 1 folder of our Blackboard class, you'll find that listed there. If you are attending the class remotely, then what you can do is after you've written up your solutions, well, you got a couple options. Number one, you could just type it up in some kind of way and send me an electronic document. That's fine. But if you want to write it up by hand, as long as it's neat enough that I can read it, then if you scan it and send me a PDF or whatever document by email, as long as it gets to my account by class time on Tuesday, that will be fine. And I am very much in hopes that we'll get this technology working and you'll be able to connect with us live on Thursday. But if not, there will be another recording. All right. Well, thanks for sticking with me. And that's the end of the first lesson.